All right, everyone, welcome. So, have you ever really stopped to think about what is physically happening inside a wire when you flip a light switch? Well, today we're going to demystify all of that. We're going to get to the bottom of electric current, building up the ideas piece by piece, so that by the end of this, you'll be able to look at pretty much any circuit and understand exactly what's going on. So, here's our game plan. First, we'll tackle what a current actually is. Then, we're going to dive into the one law you absolutely need to know, the law that governs it all. After that, we'll figure out what actually powers the whole thing. And to wrap it all up, we'll learn the essential tools for breaking down even the trickiest circuits.
Okay, let's just dive right in. Section 1. First and most important question. What exactly is an electric current?
Well, at its heart, it's actually incredibly simple. An electric current is just charges that are moving. That's it. I want you to picture water flowing in a river. When those electric charges are flowing, boom, you've got yourself a current. But not all currents are created equal. You have these two extremes, right? On one hand, you've got something like a bolt of lightning. That's a wild, chaotic, massive burst of charge, totally unsteady. And on the other hand, you have the smooth, continuous, predictable flow we use every day. Like the current coming from a battery that keeps your flashlight on. So that steady flow is the one we really care about for building things. How do we make sense of it? How do we predict it? Well, there's basically a rule of the road for electricity, a single incredibly powerful law that tells us how these steady currents behave, and that is the famous Ohm's law. So this guy, George Simon Ohm, had this major breakthrough back in 1828. He figured out this beautifully simple relationship between what we can call the push, the flow, and the pushback in any circuit. This idea, it's the absolute cornerstone of all circuit analysis. So, to really get what Ohm was talking about, we have to meet the three main characters in this electrical story. And that water analogy we started with, it's going to work perfectly here. So, let's ask, who are these three key players? First up, you have voltage, which we represent with a V. Voltage is the push. It's the electrical pressure that forces the charges to start moving. Just like with water, more pressure means a stronger push. Second is the current itself. We use the letter I for this one. This is the flow. It's the actual amount of charge that's moving past a certain point over a certain time. We measure it in amperes, or just amps. It's really no different than measuring how many gallons of water are flowing through a pipe every second. And third, we have resistance, or R. This is the pushback. It's basically anything that gets in the way of the flow and tries to slow it down. It's like trying to force water through a really narrow or rusty pipe. And we measure this resistance in a unit called ohms. And here's the magic. This is how they all connect. The push, voltage, is equal to the flow, current, multiplied by the pushback, resistance. V equals I times R. This simple, elegant little formula is the heart and soul of Ohm's law. It's the key to solving a ton of circuit problems. Okay, but wait a minute. This brings up a really good question. If you just have a piece of wire, the charges don't just flow on their own. They neutralize, and everything just stops. So, what makes the current keep going in something like a flashlight? What's the engine? Well, the answer is something called electromotive force, or EMF for short. And this is the job of a battery or a power source. You can think of a battery like a pump for electrons. It's constantly doing work, taking those charges from a low energy point and lifting them back up to a high energy point so they can flow all over again. Now listen up, because this is probably the most important and confusing thing about EMF. Despite having the word force right there in its name, it is absolutely not a force. It's actually a voltage. It's the energy supplier for the entire circuit, turning the chemical energy stored inside the battery into the electrical energy that keeps that steady current alive. Okay, so we've met all our key players: voltage, current, resistance, and the EMF that powers them. But what happens when our circuits get, well, messy? With multiple loops, a few different batteries, suddenly just using Ohm's law by itself isn't going to be enough to figure out what's going on. For those really tricky situations, we've got to open up our toolbox and pull out something a bit more powerful. And that's where we turn to a couple of rules from a physicist named Gustav Kirchhoff. And what's so amazing about these rules is that they work for any circuit, no matter how complicated it looks. And the best part? They're based on ideas that are just fundamental to how the universe works. The first one is the junction rule. It's just conservation of charge. It says whatever amount of current flows into a point where wires meet, that exact same amount has to flow out. Simple, right? Charge can't just vanish. Then there's the loop rule. This one is all about conservation of energy. It just means if you take any round trip, any closed loop around a circuit, all the voltage gains and losses have to add up to zero. You always end up right back where you started energy-wise. So let's just quickly recap the essential tools that are now in your toolkit. First, you know that current is simply charges on the move. Second, you've got the master equation, Ohm's law, V equals IR, to relate voltage, current, and resistance. Third, you know that an EMF source, like a battery, is the engine that drives a steady circuit. And finally, for the big, complex puzzles, you have Kirchhoff's two rules to guide you. All right, I'm going to leave you with one final little puzzle to think about. We know for a fact that individual electrons in a wire move incredibly slowly. I mean, literally slower than a snail's pace. So how is it possible that when you flip a switch, the light across the room turns on instantly? Think about it. What is really happening in that wire the moment that circuit becomes complete?